Have you ever scrolled through the infill settings in Bambu Studios and wondered, what do all of these actually do? Grid, gyroid, cube, honeycomb. They all look different in the previews, but what really changes inside your print when you switch between them? So I took it upon myself and printed them all. Same model, same filament, all 15% infill. The only thing that changes is the internal geometry. This is a simple overview. We're going to be looking at the infill pattern and how it builds inside of my parts. And if you'd like to see these put under stress, snapped, crushed, or properly load tested, let me know, and that is something I'll work on next. Infill does three main things. First, it supports the top layers so they don't sag. Second, it adds strength and rigidity to the part. And third, it controls weight and material usage. The higher the percentage, the more material inside, but the pattern you choose changes how that material is arranged. Infill does three main things. First, it supports the top layers so they don't sag. Second, it adds strength and rigidity to the part. And third, it controls weight and material usage. The higher the percentage, the more material inside, but the pattern you choose changes how that material is arranged. Two prints can both be at 15% infill, but behave very differently depending on the geometry of that internal structure. So if the percentage controls how much material is inside the part, the pattern controls how that material is arranged. Let's start with the 5 most commonly used infill patterns and see how each one builds inside differently. Grid consists of 2 sets of parallel lines that intersect at 90 degrees, forming a simple crosshatch mesh inside the part. It's one of the simplest and fastest infill types, which is why it's often used. Because those lines cross over each other, you get a lot of intersection points. That can cause a slight material buildup where the layers overlap. And at higher print speeds, those raised intersections can sometimes lead to a bit of nozzle scraping or extra noise as the printhead passes over them. Gyroid is a type of a 3-period minimal surface, often shortened to TPMS, which means it's a continuous, repeating 3D surface that flows through the part. Instead of straight lines or sharp intersections, gyroid forms a smooth, spiral-like lattice that supports the model in all directions. Because there are no intersecting lines within the same layers, the nozzle doesn't repeatedly cross over the raised points, which helps maintain a smoother motion during printing. However, the path is more complex. That means slicing takes a lot longer, and G-code files are larger. At higher densities, especially at high speeds, the consistent curve motion can introduce a vibration compared to similar patterns. Cubic creates a 3-dimensional lattice made up of cube-like structures positioned corner down throughout the model. This orientation creates numerous internal air pockets which can help with insulation and in some cases even buoyancy. Because these structures repeat evenly in all directions, Cubic provides a relatively uniform strength distribution across the X, Y, and Z axes. It's often chosen when you want a good balance between structure, performance, and printing efficiency. Rectilinear prints a single set of parallel lines per layer, then alternates the direction on the next layer. Because it only prints in one direction per layer, the toolpath is shorter and more direct. This helps improve print speed and slightly reduces filament usage compared to more complex patterns. Since the structure doesn't build a dense multi-directional lattice, it's generally used for models that don't require high structural strength. It's very simple, effective, and predictable. Concentric creates a series of parallel loops that contract inwards from the outer wall of the model. Each layer follows the perimeter and gradually moves towards the center, rather than forming a crosshatch or lattice structure. When printed in transparent or translucent materials, this pattern can create a really clean, layered visual effect inside the part. However, because the lines don't intersect, or reinforced across the layer, it has a lower load bearing capability horizontally compared to vertically. So, it's not ideal for parts that will experience significant side-to-side stress. Concentric is more about shape following structure and visual appeal than multi-directional strength. Those are the 5 infill patterns most people tend to use. Now, let's look at some of the other options available to us. Starting with line. Line uses straight lines as its only basic filling unit. There are no curves or spiral elements involved. Unlike rectilinear, the lines aren't simply parallel and alternating directions layer by layer. Instead, they can be arranged in a mesh-like or interwoven structure, forming a more complex three-dimensional support layout. Because of that, line can create strong basic structural elements while still keeping the geometry relatively simple. Its straightforward pattern builds entirely from straight segments, but arranged in a way that provides more reinforcement than you might expect. Triangles form a repeating triangular mesh throughout each layer. One of its key advantages is its shear resistance. Because triangles are inherently a rigid shape, the pattern provides relative uniform strength across all horizontal directions. However, the geometry often creates longer unsupported spans beneath the top surface. That means the top layer may need to bridge larger gaps, which can require additional top layers to achieve a smoother finish. At higher infill densities, the frequent intersection points can also restrict material flow slightly, which may reduce overall strength if printing very dense. While triangles offer strong planar stability, it does have trade-offs depending on surface finish and density. Tri-Hexagon is formed up of 3 sets of intersecting parallel lines. Together they create a repeating structure made up of smaller triangles and larger hexagons within each layer. Like the triangle pattern, this design provides excellent shear resistance, but the additional geometry does increase a reinforcement across all horizontal directions. Because of that, the triangle hexagon is considered one of the stronger infill patterns when dealing with tensile stress. Another advantage is that the short connection lines between the infill and the model walls. These shorter spans can help reduce warping caused by uneven cooling. So, Tri-Hexagon combines a strong planar reinforcement, which improves structural stability during printing. HoneyComb mimics the natural structure of beehives, using the repeating hexagonal cell to form the internal pattern. This geometry creates a lightweight but rigid structure, and unlike many lattice patterns, the cell doesn't intersect within the layers. Because of the way hexagonals distribute force, honeycombs can significantly improve rigidity and impact resistance. However, this pattern typically uses around 25% more material than many of the other infill types. And because the way the toolpath is more complex, both slicing time and print time can increase. So, HoneyComb provides strong structural performance, but with a trade-off in material use and printing efficiency. Adaptive cubic is similar to the standard cubic infill, but instead of maintaining the same density throughout the entire model, it automatically adjusts the internal density based on how far the area is from the model walls. Closer to the walls, the structure becomes denser to provide stronger support. Further inside the model, the pattern becomes more open, reducing material usage and print time. This approach helps maintain a stable support for the top layers while avoiding unnecessary material inside the center of the part. Because of that, adaptive cubic can help prevent top layer collapse while still keeping the print efficient. Aligned rectilinear is formed by parallel lines running in the same direction. Because the toolpath is simple and direct, it helps save both time and material during printing. However, if the direction of the top layer matches the direction of the infill underneath, there may not be enough support between the lines. That can cause the top surface to sag or fall slightly between the gaps. So while aligned rectilinear is efficient, it can sometimes require careful orientation to maintain a clean top surface. 3D honeycomb. Like the standard honeycomb, this pattern is based on hexagonal cells, but instead of forming a flat structure in each layer, it builds a three-dimensional framework throughout the model. Because of that, the infill density is generally lower than the traditional honeycomb, which can help reduce printing time. As that printing progresses, the pattern rapidly changes direction along the z-axis. This creates a true three-dimensional structure that improves connectivity between layers. So compared to regular honeycomb, 3D honeycomb focuses on the spiral structure and internal layer strength rather than purely planar pattern. The Hilbert Curve is a complex continuous path made up of many right-angle turns. The pattern fills the space by folding back on itself repeatedly. Because of the large number of turns and directional changes, both the slicing and printing can take longer compared to similar patterns. However, the continuous path helps distribute internal stresses more evenly throughout the model. It also creates a very distinct internal texture, which can contribute to smoother surfaces on lightweight prints. Because of that, the Hilbert Curve is often suited for lighter models, and surface quality is important. Archimedes chord is a pattern based on a mathematical curve known as Archimedes chord. Unlike many other infill patterns, the path doesn't intersect within the same layer. Instead, the toolpath continues smoothly in one direction across the model. Because the printer doesn't need to consistently change direction, the motion can remain more continuous and controlled. This also helps avoid the buildup of material that can sometimes occur at the intersection points in other patterns. So, Archimedes Chords focuses on smooth, continuous motion while maintaining a clean internal structure. Octagonal Spiral. Similar to the Hilbert Curve, the pattern follows a continuous path, forming a zigzag spiral structure within the octagon layer. The pattern creates large internal sections, giving the infill a very distinct visual appearance. Because the structure focuses more on the spiral path than the strong cross connections, the overall structural strength is relatively low. There are a few strong connections between layers, which means the model can be susceptible to horizontal deformation. So while the octagon spiral has an interesting aesthetic structure, it's generally not intended for parts that require high mechanical strength. Supporting cubic. This pattern gradually increases the number of internal triangular structures as the print moves upwards through the model. As the height increases, the internal framework becomes more reinforced. Because of the way the triangles build and connect through the structure, supporting cubic provides stability across the X, Y, and Z directions. That makes it suitable for models that need to handle forces coming from multiple directions. It focuses on maintaining structural stability throughout the part rather than keeping the density uniform everywhere. Lightning infill is a minimal pattern designed specifically to support top surface of a print. Instead of filling the entire interior, the print forms a serrated tree-like structure that grows upwards towards the top layer. The infill density only applied directly beneath the top surface, providing support exactly where it's needed. Because of that, Lightning can dramatically reduce both print times and material usage. However, it offers very little structural support, so it's not intended for parts to handle load or mechanical stresses. It's best suited for decorative parts or aesthetic models, where strength isn't a priority. Crosshatch is created by arranging the toolpaths of the adjacent layers so that they intersect each other. Within a certain range of layer heights, the printer can maintain the same filling direction before switching orientation. By reducing how often the printer needs to change direction, this pattern can shorten the overall print path. That helps reduce the printing time while still creating a basic internal lattice. Because the structure is relatively simple, it generates the best suited for non-load bearing parts or rapid printing scenarios. So crosshatch focuses more on printing efficiency than structural strength. The zigzag infill is made up of continuous straight lines arranged in alternating directions within each layer, creating a zigzag pattern. The appearance of the pattern can also be adjusted by changing the infill rotation step between layers. Because the nozzle can extrude continuously along the path and printer minimizes the retractions and pauses, this can help increase printing speed. Interestingly, when you handle the print, the structure can feel slightly flexible, almost like TPU, even when printed in a rigid material. If the rotation angle is set to 0, the pattern will closely resemble rectilinear infill. However, the structure itself provides low structural strength, so it's generally used for parts with low load bearing requirements. Zigzag focuses more on efficient printing more than structural reinforcement. Cross-zag. Traditional rectilinear infill typically creates a perpendicular crosshatch pattern layer by layer. Cross-zag builds on this by introducing directional control at the intersection points of that crosshatch structure. By adjusting the infill shift step, you can change the orientation of those intersections and gain more precise control over how the internal structure is arranged. If the infill shift step is set to 0, the pattern becomes very similar to a standard rectilinear infill. So cross-zag offers a more adjustable variation of the classic crosshatch style infill. Locked zag builds on the zigzag style infill pattern but adds additional connections that effectively lock the structure together. These connections help stabilize the pattern and prevent the lines from shifting within the layer. Because the internal paths are more tightly connected, the structure maintains better cohesion compared to similar zigzag style patterns. In particular, it's useful when you want the surface texture you can get from cross-zag, but with additional structural strength. It can also strike a nice balance between aesthetics and durability. For example, it can be useful for high-stress prints like footwear or flexible structural parts. LockZag actually has its own dedicated page on the bambulab wiki, so if this is something you would like me to explore in more detail, let me know in the comments and I'll have a look at making a video on just this one pattern. 2D Lattice creates a repeating grid-like structure across each layer, forming a network connected cell. Unlike some of the more complex three-dimensional infill types, this pattern focuses on building strength within the horizontal plane. The interconnected layout helps distribute force across the layers while maintaining a relatively simple internal structure. Because of the balance, it can provide a stable support while still keeping the toolpath relevantly efficient. So 2D Lattice offers a straightforward structural pattern without the complexity of the more advanced infill geometries. So that's all the infill patterns currently available in Bambu Studios. To make things easier to compare, here's a quick reference table that shows the main pros and cons for each pattern. As you've seen, each pattern changes how the printer builds the insides of your model, from fast, lightweight structures to a more rigid multi-directional support. To make things easier, I've also uploaded the test model to MakerWorld so you can print the same samples and explore the infill patterns yourself. The link will be in the description. There's a particular infill pattern that you'd like me to explore in more detail, please let me know in the comments and I can take a deeper look. And if you found this video useful, remember to hit the like button, and if you're new around here, please consider subscribing for more 3D printing guides and projects. And thanks for watching, and I'll see you guys in the next one. Bye.